Uh, Today what we're going to do is mainly unsaturated hydrocarbons. Unsaturated hydrocarbons have double, triple bonds. Physical properties are similar to those of saturated hydrocarbons. But the chemical properties are different because there's a double bond here which is reactive. Okay, we're going to talk about that. Chemically, saturated hydrocarbons are stable, but the unsaturated are reactive. Now there are three types of unsaturated hydrocarbons. First one is called the alkene. Ene now, not ane. The last name ene end with alkane, end with the ene means it's a double bond. At least one double bond is there, right? Ene means Y-N-E-S. Enes means contain one or more carbon-carbon double bond. Genes means Y-N-E-S. At least contain one carbon-carbon triple bond. Now we're going to talk about aromatic hydrocarbons. They're different. Let me show you one structure. How many aromatic hydrocarbons have how many double bonds? 3. But they're in a 6-membered carbon cycle, right? Alternating double bond. Okay, when you contain at least one of these or many of these in the molecule, the molecule is called aromatic hydrocarbon, right? Normally, alkenes and alkynes, they're related to alkenes, but they are not in a alternating double bonds here, alternating with single bond, double bond, alternating with single bonds here, right? They are aromatic, especially when they are in a 6-membered. Right? Now, you understood some characteristics of unsaturated hydrocarbons now. Before we get into problems, let me go through this a little bit. Relevant questions. Like alkanes, we can have unsaturated alkenes, alkynes, and cycloalkenes. That ene means double bonds. At least one double bond is there, right? And also now we have to understand how we name them. It's different, little different from naming alkane, but similarities are there. Okay. Everything we learn about alkanes, like line angle formula, how we draw line angle formula for alkenes, and some description of where the alkenes are formed, physical properties, chemical reactions of alkenes. And we're going to do today up to here, alkynes. We're going to basically talk about alkenes and alkynes and their reactions. Now, we're going to start on aromatic hydrocarbons, where you have a 6-membered carbon atom ring with alternating double bonds. 3 alternating double bonds, single bonds. So we're going to talk about that. There are similarities in naming alkyne and alkene, right? Again, you pick the longest chain. One of the things we do is for alkyne, the heptane become heptyne. If it is alkene, this will be heptene. Right? So rest of the thing is similar, right? Right. Remember we ran into a naming problem. Are you back naming? Now, you asked me a question about that alphabetical order. alphabetical order. Now I read everything, and I found out what is the easiest way to explain this. All right? This is nothing to do with the branching right now. Branching we cleared out, right? First branch get the lowest number, all right? But when you're naming, writing the name. For example, remember what we had was this. We were trying to remember, name this. We call that cyclohexane. Okay, cyclohexane. Then we try to identify the methyl group. Okay. Then you write third butyl group here. Now, point is this. In the book and other literature, this third part is italicized. It's in italics. What do you call it? Italicized? Italicized. So therefore, whatever, like a sec, all right, third, die, okay, all these things are in italics. Therefore, they are not counted for alphabetic naming. All right, the alphabetizing the name. All right. So in this case, we were lucky. All right. This group here. Now, like you said, what is the idea here? This will get, because when you have two groups here, whatever the alphabetical order, this gets number one here. Okay. Now this is going to be one third butyl. This is going to be 1, 2, 3, 4 methyl, right? Therefore, when you're writing down the name, it has to be 1 third. I will put a underline here because I cannot write italics here. Butyl, then 4-methyl cyclohexane. That's what we got there too, right? For own reason. I mean, I gave a different reason. Now you understand if you are naming how to alphabetize. The alkyl group name is the one that should be looked at, not the di, tri, or third, sec, things like that. All right. Any question about that now? Okay. All right. We are continuing on group homework 2. Now, one of the other thing I wanted to show you is this double bond creates a molecule where you have a rigid structure. Okay. For example, when you have a double bond like this and a single bond like that here, the single bond you can rotate freely, right? So we describe it as single bond show free rotation around the bond, right? This is important to understand the conformation, right? But now, if you have a double bond somewhere here, you cannot rotate. Therefore, it constrains the molecule. If you have two different groups here, this side or same side, it's the same molecule, it's a different conformation. But this one here, if you have a double bond, you can remove this green balls. Put this green ball here, and you get a cis isomer and a trans isomer. These are called geometrical isomers. Geometrical isomers come from molecules when they have a double bond or a ring. We're going to talk about this. And because of this double bond, this isomerism is called geometrical isomerism. And this is going to be trans isomer. And also you have to pay attention to the bond angles. Now, in 120, how many of you remember that sp2 hybridization? sp2 hybridization. There are going to be different hybridizations. sp give a linear structure. sp2 give a triangular structure. Do you remember those? And tetrahedral is sp3, right? So because of the double bond, there are 3 single bonds, and on top of one of these double bonds, first one is single, then on top of that there's a second bond. That's how you get a double bond. Then double bond came from overlap of p orbitals, unhybrid. You don't have to know all these details, but at least you have to know this is 120, right? And this double bond is different from the single bond because it doesn't show free rotation of the 2 carbon atoms, okay? Making it. The double bond carbon atom, which making the double bond have sp2 hybridization. Right. Single bond carbon atom, single bonded carbon atom has sp3. And the triple bonded carbon atom has sp hybridization. Okay, sp. So that is the if. Now, other thing I want to show is applications of unsaturated hydrocarbons. The first one is carrots. It has beta carotene. Why you need carrot for? What is it related to? Site? Yes. The carrot contains a compound that later in the body converted to vitamin A. Okay. It's also called retinol. We're going to look at this later. It's associated with vision. Okay. That molecule contains about 4 double bonds in a chain and a cyclohexane ring. Okay. The other one is ripening. Other application is in ethene. Ethene is that cause tomato to ripen. Now this is being used in Walmart. When you transport produce, you cannot transport them in a ripened form, like a banana, so there's tomatoes, okay? They pluck green tomatoes, okay? And they transport to the grocery store, and grocery store has a room where you can gas them to with ethene. Ethene is ethylene. Ethylene is a common name for this. Ethylene, the IPAC name is ethene, this is the common name. The structure is this. Simplest alkene. Right. This one is interesting because where I come from, I'm originally from Sri Lanka, and we used to do this. When you have some festival, we need to have bananas, right? Ripened bananas. So we need to get them ripened on a particular day. We cut the green ones, and we dig a hole in the ground, okay? and cover with the leaves and some poles and the leaves, then put some soil on it, make it sealed, all right? Then we make a hole, all right? Then what we do is we smoke, pass smoke into it. Smoke is when you burn organic compound, that gas is the smoke. When you burn organic compound, it contains, part of it is ethane, right, ethylene. Therefore, what we had to do is every morning, as a small kid, I used to watch them doing it. They go and smoke it this morning, and the afternoon, and the next morning, and they open up a little bit. Oh, it's not ready yet, and go doing it, right? So we get the ripened banana. It's a Walmart, basically, like a crude Walmart gas chamber, right? How many of you work for Walmart here? Anybody work for Walmart? I've never seen one, here. I assume they have ethylene tanks and that enclosed, room space and just do it. Okay, the other one is acetylene. Acetylene is common name. It's written down here. Acetylene is a ene. This would be common. The IPAC name is ethyne. Ethyne. Et means two carbon, right? Ethene bonded compound with two carbons. Ethyne. Now, you guys seen it with the oxygen flame. A lot of people do welding, right? Oxyacetylene flame. It get a higher temperature than natural gas flame. You can even do quartz. Quartz is not, it's special form of glass, quartz. It needs to be heated to a very high temperature to melt it, bend it, glass blow. Quartz is done with the oxyacetylene flame. All right. Now this one is another application of unsaturated compound. What is a pheromones? Sex pheromones.
Smell produced?
Say that again.
Is it smell produced by the body?
Yeah, smells produced by bodies. That gender specific, right? Like, in the world of animals, like insects, dogs and cats and dogs, their sexuality is manifested by pheromones, where even though all the dogs around here, if I have a dog, if she's in heat, every dog in the area knows it, right? They try to jump up the fence and all that. And also insects, right? How they made is they smell the female pheromones, then go there, and it's one of the drives, in the living systems, right? To procreate, you have to. It's kind of incentive. Anyway, what you do is you can create artificial pheromones. Some of the compounds, unsaturated compound, book has one of the structure of one of these compounds. Insects get attracted to this. I have a friend who made a living on this. He worked for a company in California. He's an organic chemist. He could make this unsaturated compound. He had the procedure, then he make like a kilogram of this, with big this in a big flask. Then he made small traps, and put a little bit of that and sell it to different farmers, right? So they keep them in the field. Now what happened is they go in there and because they got attracted, I think that at the same time this trap also has a poison or sticky substance, then they cannot leave, after they come there. So in a way, you stop mating, right? then you stop proliferation of the insects and preventing that. I think it's better than doing in a pesticide, right? Okay, environmental friendly, right? So you got some idea about the applications. Isomers are compounds with the same chemical formula, but the different molecular structure, right? So there are so many ways that the molecular structure could be different. One of these ways is constitutional isomers. That means connectivity is different. Like we have an example of butane, right? Butane could be linear, then the branch is isobutane. And we also talk about pentane, isopentane, and neopentane. They have completely different properties. Also, another example is alcohol and dimethyl ether. Remember, oxygen stuck between two methyl groups. So those are constitutional isomers. Now we have to talk about the other types of how the molecular structure is going to be different. The next one is conformational isomers. This is coming from rotation, single bonded carbon atoms. Okay, if you create for example, I'm getting the butane molecule here, normal butane, right? Now I want you to focus on this bond here in the middle. You can rotate stuff here, all right? These groups are hitting each other. Okay, that one, when the if you write it, there are different ways to write it. You have this, like this. It's called eclipse. What do you mean by eclipse? Online with each other, right? Eclipse is like a sun and the moon, like they are lined up. This has more energy because of the repulsion, right? This is one of the conformations. First, let's draw it like this, and you have that. Okay. This is the eclipse conformation, and if you have CH3 groups here, two CH3 groups, because these are the two carbon atoms, right? This is called. This would be staggered conformation. Staggered means they are apart. Okay. Okay, eclipse means like this. Okay, staggered means like this. Now, for if you have only hydrogens, which conformation? I mean, if you have only hydrogen, right? This is going to be higher energy than staggered, because these two hydrogens are getting close to each other than in the staggered conformation. The energy is a little different. Okay, it's very minute. Okay, but still those are called conformations. They're not real significant conformation, but they exist. Now, if you had two methyl groups, now you're going to have different conformations, right? Which one would be more stable? Let me draw this one. You can figure this out. That's a CH3 group. Rest is hydrogen. Okay, now this is another CH2 group. Which one is, this is the staggered conformation, all right? Staggered conformation here, and like that, and this CH3 group is here. Now, which one is more stable? The syn or anti? Anti, because their methyl groups are far apart. Like I was trying to show you at the beginning. Right. Okay. Now, I'm going to talk about a little later about this conformation of cyclopentane. Now, this conformation is called envelope conformation, envelope, because you have like a flap here. Let me draw it here. C5, H10. It looks like this. Line formula. Okay, this is one of the conformations. See, they can rotate around the bond. This can flip here. They have the same energy. But it's still the rotation is between single bonds, right? Now in the cyclohexane, you have a port conformation and chair conformation. I'm going to talk about that a little later. Those are the rotation around a single bond. How many of you understood it? There are minor energy differences. Now you have another way to create different molecular structure. They're called different from constitutional isomers, and these all are called stereoisomers. Conformational isomerism, geometrical isomerism, and optical isomerism are called stereoisomers. Isomerism. Connectivity is the same, but because of a double bond constraint here, put on the 2 carbon atom, there's no free rotation. Therefore, you get here is restricted rotation around carbon-carbon bond or ring. The ring also create a restriction here. Now you cannot free rotate a little bit, little freedom, but not total freedom. Okay, it's called geometrical stereoisomers. Now stereoisomers have the same connectivity, right? Bonds are not different. So an example is this. Here. This one is called cis. Cis is same side, cis 1, 2 dichloroethene. Why is ethene? Because it's alkene. All right, the other isomer is this, geometrical isomer. Because of the restriction placed by, imposed by the double bond or later we're going to look at the cyclohexenes. Okay, this one is opposite, it's called trans. Trans 1, 2 dichloro ethene. Now you can identify if you have a double bond and 2 different structures, that means geometrical isomers. For a ring, then you have restricted rotation, then it's geometrical isomer or stereoisomerism. Okay, now this is a little complex. We're going to talk about this a little more in dealing with biochemistry. Let me show you something. Thought I had another one. Okay, I do. But now I want to emphasize. How many of you have a model set? You could buy on Amazon.com or bookstore. I used to have it. Just go and check it. Okay. Now the optical isomerism I'm going to talk about. It's easy to understand these things with the models, even with these, rotations and all that. Now there's a carbon atom here in this molecule, right? I'm trying to explain the optical isomerism. Okay. Now, this carbon atom is attached to 4 different groups. See that? It could be chlorine, bromine, fluorine, and hydrogen, right? So 4 different groups. Now, when a carbon atom is attached to 4 different groups, sp3 hybridized carbon atom, is called an asymmetric carbon atom. Okay, let me write down this word. Right. Now, something related to this is this. My 2 hands are mirror images of each other, right? But can I superimpose them? That means exactly no. When I try to rotate it, these are also called chiral carbon. Chiral means handed, handedness. Excuse me. Handedness. What it got to do with this? What is this? Why is this important? Now, if I have right-handed glove and a left-handed glove, would this left hand, right hand would fit in left hand glove? No. Some cheap gloves, where there's no handedness, symmetrical, right? Would fit. But same apply to here. This chirality also explained by chiral carbon atom. Now, if you look at this, if you put a mirror in between these two, let me see. Okay. No. Okay, let me show you this. These two are same molecule. Why I'm saying this is same molecule? Because if I rotate it, I can superimpose it, right? There's no handedness. This is the same 2 hands. Chirality is the same. Now, if I change this ball with another ball, okay? Hope I did it right because the 2 fell off. Okay, now it's the same thing. Okay, if I change this one to that one, okay. Okay, now I try to superimpose. The reds are coming together, then the blues, and they are not fitting. Now, what is the common thing about this? If something cannot be superimposed, like my hand, there are mirror images, right? The molecules also follow this idea. There are left hand, dextro means clockwise, levo means anti-clockwise. Now these molecules rotate light, plane polarized light, by a certain angle. But this one does it this way, this way. Therefore we can, if we have a pure mixture of this and this, we can tell which one is which. That D and L. Now, this is the interesting thing. In our body, you have D-glucose. D-glucose is the one we have. That's a L-glucose, the mirror image of glucose. But amino acids are, I forgot which one, okay? I think amino acids, you remember amino acids? Body has only one type, okay? I think L amino acids, right? I need to check that. Anyway, what we have is, because of the asymmetric carbon atoms, for example, D-glucose and L-glucose are different things. We don't find this in our body. And it's also something to do with enzyme activity. Enzyme has to fit, the substrate has to fit in the enzyme. It's called key and lock mechanism, right? You put the key, then the enzyme fits. Substrate fit in the enzyme and do the chemical reaction. Point is, if you can create this L-glucose, it may be sweet, then it will be artificial sweetener. Why? We cannot digest L-glucose, right? But who's going to make it? It's very hard to make glucose synthetically, L-glucose. I mean, the plants been doing this for ages, right? D-glucose. So, right. How many of you got the idea about this isomerism now? We're going to talk about them in the other classes a little bit. Yes?
Wait, you said the mirror image one is the optical isomer?
Yes. When a carbon atom contains 4 different groups, they have a asymmetrical or chiral carbon atom. They give rise to mirror images of molecules, right? For example, if you have two, if these two groups are same, okay, at least if you replace with this, you destroy the optical activity. There's no optical activity because this is mirror image, right? But you can superimpose here. The chirality comes from the 4 different groups, right? Attached to carbon. We're going to talk about this, at least you got an introduction, right? Okay. Now describe the conformational isomerism in following alkanes. What is conformational isomerism? Conformational. It's coming from what? Rotation about carbon-carbon single bonds. All right. So what did I write last time? Either this way. This is called staggered conformation. Okay, this is staggered. Okay, and this is this is called projection formula. I think it's called Fisher projection. How do I come up with that? This will be the one. Yes. Okay. This. Here. That way. Here. The carbon, two carbons are, one is here, other one is behind it, and this is called anti-conformation, right? Anti-staggered conformation. We don't talk about eclipse. Why we don't talk about eclipse? Eclipse is high energy, right? So this one is when the CH3 group is here, then we call it syn. just to get you to understand their conformations, right? That's the most important thing. Because sometimes we talk about conformations, you know, you need to know that. Now, cyclopentane, this is the annular. So this rotates like this here. Kind of, they're same, you know, they can like flip up and down, you know, here. In the molecule, when they're in the solid state solution, they kind of. You might think all these molecules are boring things, you know, they may be doing a lot of other things we cannot see, you know. I mean, at least something we can see, right here. Now I'm going to create the cyclohexane conformations. Now let me tell you, which is this one? Board or chair? What do you mean by a chair? Now in the drawings, what we can do is this. Like, isn't it look like you're sitting down here on a chair, you know, in your poolside, you know, chair. This is the, where you lean, this is for your legs, right? That's called chair conformation. Now, what this would be called? What it look like? Okay, you rotate it up, okay, here like this. Okay. What is it called? Boat? Doesn't it look like a boat? All right, which one is more stable? Chair or the boat? Chair. This one has, you know, these two hydrogens hitting each other. So therefore, the stable conformation is. So sometimes they go through this, go there and then they go do flipping. But that is high energy, right? Now you understand alkanes could have conformations, right? Rotation around double bond, single bonds, and different structures. I mean, they are not really real isomers. Conformational isomers are not considered very real. I mean, they are transitory and they are momentary, so they pass from one to the other. Some of them have high energy. Calculate the units of unsaturation in following hydrocarbons. Okay, what is units of unsaturation? Or what is saturated? I'm asking what is saturated?
Alkanes.
Alkanes. So they all contain what? Single carbon bonds, right? Now, then unsaturation means you have double bonds, triple bonds, like that, okay? So therefore, how do you create a double bond in from an alkane? How do you create a double bond? For example, if you take, okay, let's stick with this simplest molecule. This is ethane. How do you create a double bond? You remove this to, right. I mean, we have a molecule that we have already created here. Okay. If you remove two hydrogen from here, from the alkane, then bend it up here, and you create the right. So what is how many units of unsaturation? 2 hydrogen is equal to 1 unit of unsaturation. So therefore, definition of unit of unsaturation is number of hydrogens removed from a hydrocarbon alkane. Number of hydrogens. Hydrogens means H2, right? Hydrogen. So that is the definition. So number of hydrogen removed. Okay. Now this one, you see the you first check this CN, HN, 2N plus 2. Okay, if you calculate it, 4H10 is okay. That means there's no hydrogens missing, right? Therefore, unit of unsaturation, what is that? 0. Okay. Now, cyclopentane. Now, you want to make a cyclic alkane. We need to remove 2 hydrogens from. I have shown this before. So this is pentane, and to make a cyclopentane, you have to remove these 2 hydrogens, right? So then then it becomes cyclopentane. Okay. Now this one, if you check the formula, to find the unsaturation, you calculate fit in the formula here. It's C5 should be H12, right? Okay. Now how many hydrogens missing now? 12 plus 10, right? 2 hydrogens. What's that?
So is that 1 unit? You said 2 hydrogen equals 1 unit or not?
Number of hydrogens I'm talking about. Okay.
But unit of unsaturation is if 2 hydrogen means like 1 unit, right?
Yeah. Hey, we have to keep track of a hydrogen molecule and a hydrogen atom, all right?
Okay.
I mean, when you say hydrogen, it doesn't mean H2, right? Hydrogen atom is different. So, I mean, sometimes always there a place to get confused because we are using the terminology loosely, right? What I'm saying is not the unit of answer, a number of hydrogen atoms, okay? So that atoms, okay, 2. Hydrogen molecules is 1, right? Therefore, number of, right. So I was loose there too, yeah.
I thought for cyclopentane that it was 10 hydrogens.
Yeah, that's what it should have been 12.
Oh, it should have been.
So therefore, if it is, all right, I'm subtracting from it. Somewhere you have to know where this unsaturation coming from, right? You have to compare the molecular structure of cyclopentane, right? Number of hydrogen to the saturated one is 12. 12 minus 10 is 2 hydrogen. That means 1 hydrogen molecule, right? Therefore, what is unit of unsaturation now? 1. I don't want you to follow exactly what I'm doing. You have to find the idea here, right? Everybody find it differently. But at least if you got the answer, you do have to look at this. It should have been C2H6, right? And that means 2 hydrogen atoms. That means what is the unit of? This is Cn. Oh, otherwise this is this, and this is Cn, Hn, H2n. Yeah. Now the molecule with 1 double bond or cycloalkane always has one unit of unsaturation. Now benzene. Benzene is called trilene cyclo 135. This is the benzene. 1, 2, 3, 4, 5, 6. Okay, 4. Why do you call it 135? Now remember, when you have more than one double bond, you have to name them. This is means like a trimethyl, trigens means 3 double bonds. Now you have to tell where they are located, right? Yeah. Okay, benzene is the common name. Now, what is the unit of unsaturation now? Let me see whether you guys. Wrong. 4. For the cycle 1 and the 3 double bonds 1, right? Each double bond is a 1 unit of unsaturation. Okay, there's a cycle 2. The ring is formed. 2 height. Okay, unit of unsaturation is 4. Okay, what is the unit of the unsaturation in this molecule? I'm trying to see whether you guys understand. What is in acetylene or ethyne? What is unit of unsaturation? How many units are? 2. There's no ring in there. Therefore, this 2 double bonds. Okay. 1 double bond is 1 unit. Man, we did it. The number 2 is over, right? Okay. Now let's do some quiz. Number 2 is quiz number 1. Let me put it down. A cycloalkane having only 1 carbon double bonds will have a general formula. You have to understand, generally no unit of unsaturation I have to have CN 2n plus 2, right? So then you remove, that's how the formula is related here. How many of you got the answer? Number 3. Let me explain this one. Not a question. What is the IPAC name for this? Okay, how do you label it? You have to do it before that. Now, according to the IPAC, for naming alkenes, which way longest chain? Longest chain is 1, 2, 3, 4, 5. It's 5-member chain. Now, which way we label now the carbon atom? Number the carbon atom. But now this get the priority. Carbon-carbon double bond. It's more reactive, right? Let's get the priority. So these carbon atoms should get the lowest number. That means I do this way, 3, 4, 5. If I do this way, 1, 2, 3, 4, 5. See, these are now higher, larger numbers, all right? So therefore we don't do it. Give the lowest number to the carbon atom that contain the alkene, right? So therefore this methyl group is 4-methyl, right? Now, what is the answer? That has to be pentene. Not only one pentene, it had to be 2 pentene. Why? Because it's where it's located, right, on the chain. So what the answer should have been this, right? the 4-methyl 2-pentane.
Yes.
Okay. Now that's how you name, the IPAC name for number 4 is number 2. Okay. IPAC name for this. Got it? Better put the number on it, okay? There's only one way to number is molecule is symmetrical.
What number of the quiz are we on?
4 is quiz number 2. Okay, let's try 5, okay? Now there, when you have a double bond and cyclopropane, it becomes what? Okay, you have the answer. No, all these are that, right? But the problem is how you label it. Because propene methyl group could have been here, right? Then it would have to be 1, 2, 3. Okay, did you get the answer?
Yeah.
Okay.
Next question.
So I'm through the question, you're learning something here, right? Got the answer. Okay, let's move.